Okay, so let's start with the last session of today. So in the first part of this afternoon session, we have the Altarelli Prize Award. For this, I give the honor of Fred to announce the winners of this year's Altarelli Prize.
Okay, good afternoon. It's a pleasure to be here and have the opportunity to announce the winners of the Guido Altarelli Award. And this award honors the memory of late Guido Altarelli. He was one of the founding fathers of QCD, an outstanding communicator for particle physics, and a mentor and strong supporter of junior scientists. So it's a real pleasure to be able to celebrate his career and achievements at this event. And let me start by saying thank you to our sponsors. So we have 3 sponsors that have generously supported this to support the young scientists and enable them to come here and present their work. Springer EPJ, the World Scientific Publishing, and Centro Fermi. All 3 of those are very generously supporting this. So we thank, let's give them a hand, please. And a little bit of history, going back to the first International Advisory Council, Guido was one of the members, and you see that's quite a distinguished list. And he has a long history with this meeting, supporting this meeting, again, supporting the young scientists that were active in this. So I could tell you about it, but rather than me give you some of the history, we're pleased to have Professor Stefano Forte here with us, who is actually a close collaborator of Professor Altarelli. And so he's going to give us a little bit, some remarks about that. And he's a spokesperson of the NNPF collaboration, and also was a co-author and served as editor of the volume of Guido Altarelli's Legacy for my vast repertoire. So if we can switch and put him on screen just a moment. And you are on screen, and so I'll pass it over to you, Stefano. Thank you for joining us.
Okay, thanks. Thank you, Fred. I'm sorry not to be able to be there in person, but I got a lot of teaching this term, and if there's one thing I learned from Guido is that students come first. In fact, I remember when Guido was both the head of the theory division at CERN and a professor at Rome 3 University. He was probably spending more time with students at Rome 3 than the majority of his colleagues. It's a bit strange to talk about Guido within the framework of a sermon, because Guido was a very unceremonial person. He tended to take things in a very relaxed way. He did not have much patience with pompous events, and it is said that the ancient Romans would be in first-name terms with the emperor, all of them, and in that sense, Guido was a typical modern Roman in the sense of taking things always with some irony and not too seriously. But there is one reason why I'm sure that Guido would have liked to be here, which is what Fred just said, namely that Guido was almost extremely supportive of young people. I mean, I could go on for hours on end telling you stories. I remember once that a junior colleague who was my age at the time, namely in his early 30s, had both health and personal issues, and Guido did everything to get him involved in a project, both because like this, he could think more about physics than about other things, and also get started again and get some credit. Guido was always extremely generous in attributing authorship to younger colleagues. Even someone who had given a minuscule contribution to a paper will always be included among the authors. This quite in general. I mean, Guido was not obsessed by authorship, but especially it was a younger colleague, and in fact I remember an episode which involved me personally, in which some other senior colleague had not cited properly some contribution of some younger people that included myself, and what Guido did was to give him a call and tell him, look, I mean, my scientific career is such that I don't need a citation from you. I mean, he put it in a slightly sarcastic way. And then he said, however, this is something that with younger people, it is not done because they still need all of our support for their career. So, you know, in this sense, I'm sure Guido would find the right words for the winners of this year's prize. And I should like to mention one last thing, that even though I said that Guido did not especially appreciate ceremonies and honors and distinctions, of which he had many, there's one thing which he liked, especially in his old age, namely prizes. I mean, when he turned 70, he refused all kinds of celebrations. He didn't want a festship or you know, a conference, not even a dinner. But there is one thing which he said he would have appreciated, namely receiving some recognition. And in fact, some people, including myself, strive to make this happen, and he was honored by the American Physical Society with the Sakurai Prize immediately after his 70th birthday. And I think that the reason why he liked this is that he viewed the prize as a recognition of the community. So it's like, you know, being embraced by friends and peers rather than some empty ceremony. And I think that if the winners of this year's prize understand this, they can maybe also feel a bit of Guido's embrace, even though perhaps they did not have the privilege of spending time. Thank you.
Thank you for joining us, and thank you for those remarks. We appreciate it. Yeah, very nice. Thank you. So let me move on then, and let's see. This is the 9th year that we've given this award, and you see that's a very distinguished list of previous award winners, and you can go to the webpage and get all the details. So I encourage you to do that. We have two very distinguished additions to that today. But again, let me thank our sponsors, and also thanks to all of you who nominated people for this award. We have roughly 24 applicants, and it was very, very competitive, and we had extensive discussions and difficult deliberations, but we're very, very proud of the choices. I want to thank the selection committee listed there, and so they worked very hard to go through the applications, and so thank you to them. What I would like to do at this point, I would like to invite two people to help me present the awards. I'd like to invite Aaron Levy, who's the co-chair of the DIS, to come up. And also we have a very special guest with us, Massimo Altarelli of the family. And if you'd also come up, let's give both of them a hand, please. And so our first awardee is Szumila-Vance, and you see she received her degree at ODU and then did postdocs at Jefferson Labs, MIT, and is now a staff scientist at Jefferson Lab. And so we're very pleased to honor her for her outstanding contributions to investigations of color transparency and other nuclear manifestations of QCD. So Holly, congratulations. And so our second awardee is Javier Mazzitelli, and he received his PhD working on Higgs physics, and then did postdocs at Zurich and Max Planck, and is now at Paul Scherr Institute, and is a member of the LHC working group. And we're pleased to give him this award for outstanding contributions to precision calculations in Higgs boson and top quark production at LHC. So Javier. And we're just going to pause and get a couple quick photos. Let's put you guys in the middle. And, good saying that. Okay, all right, let's give another. Gotta make sure we go. Okay, thank you. Okay. All right, and now we'll have the honor of having the awardees present work, and we'll start with Holly. And so, let's see, I think it should be queued up. Maybe you can.
Very good. All right, so first I would like to begin by thanking everyone who made this session possible. It's really an honor to be here today. I'm humbled and I'm very excited to share my work with you in honor of Guido. So I'll first just begin by describing that color transparency is a very fundamental prediction of perturbative QCD. So it refers to the existence of point-like configurations in the nucleus, and we measure it by the vanishing of final state interactions of hadrons with the nuclear medium in exclusive processes at high momentum transfer. So I like to think of sort of three ingredients that have to happen to measure this effect. And so we know that the proton is a superposition of different sized Fock states. And so quantum mechanically, of course, at shorter wavelength, photons, virtual photons, are absorbed on smaller sized hadrons, right? And so we refer to this as the squeezing of that hadron through the transferred momentum. And then it has to maintain basically this small size configuration as it propagates out of the nucleus. So this happens because of the energy transfer, so boosting this particle such that it stays frozen, and the lifetime of this particle is dilated with respect to the nucleon. And finally, the strong force interaction comes at play because this small size hadron basically experiences a reduced attenuation in the nucleus. So we can think that it's color screened because these external gluon emission amplitudes from the different quarks cancel. And we can kind of think of this as having an analogous, right, to quantum electrodynamics, where you would have, an E plus E minus pair, having a very small transverse size would have a reduced cross section due to its reduced dipole, electric dipole moment. And so we can think of this as having the existence of color dipole moments. And so, really, in relation to DIS, the first indirect evidence of color transparency is implied by Bjorken scaling at small x. So particularly at small x, we have very long longitudinal distances that the virtual photon can fluctuate into hadron states. And we would expect that these hadron states would interact with the nucleon just as we would expect them to do. But we actually don't see this interaction happen. And so this is due to basically the Bjorken scaling that we see in this regime. And so it's thought that this would be basically the first really concrete evidence of these small size configurations within the nucleus. And so this would be evidence at basically the high energy. So how do we observe small size configurations at all? And so if we just want to look at them directly, we start by measuring something that we kind of are used to using, and that is we measure the nuclear transparency. So the nuclear transparency is a way of quantifying, of course, that the probability of a knocked out photon in a scattering event is deflected or absorbed. And so we experimentally define the transparency as the ratio of the nuclear cross-section per nucleon relative to that of the free nucleon cross-section. And then we can also, furthermore, define the transparency in terms of its nuclear A dependence, right, in terms of this A to alpha parameter that you see here. And so the transparency in the strongly interacting hadronic picture can be defined as such. And so if we know that the hadron nucleus cross-section has been measured out to very high momentum, and we know that the A dependence, we generally establish the A dependence as stable. And if we can account for glob or multiple scattering, so we would expect that the transparency then would have the energy dependence related to the NN scattering cross-section, which also for many of these energies then would be relatively stable and unchanging. Then we would expect that the transparency itself should not be changing as a function of the momentum transfer, Q squared. And so we can include things like nucleon-nucleon correlations and final state interaction effects that would maybe just shift the measured transparency either up or down, but it wouldn't have any effect with the momentum transfer. So any deviation then in this picture that we've established in conventional nuclear physics, any breakdown of the A dependence of this hadron nucleus cross-section or of the transparency with respect to the momentum transfer would be indicative then of the onset of quark gluon degrees of freedom. And so that's why the most interesting kind of space to look at the moment is looking for the onset of color transparency in the nucleus. So this onset, it's not known what Q squared that this would happen at, but this would be basically the evidence for the breakdown of this traditional picture. And so color transparency, looking for the onset of it in different types of experiments can kind of fall into two categories. So you can look for it in baryons or in mesons. And theory would imply that we would expect it to have an earlier onset, lower Q squared, and be more easily realized in a meson, observed, than in a baryon. And so because of the medium energies and the high luminosities needed to look for the onset of color transparency in these particles, Jefferson Lab, with its electron accelerator, is basically uniquely suited to kind of measure in this onset regime. And so historically, in the 6 GeV era, we're now in the 12 GeV era at Jefferson Lab, so historically, it was established that we could see the onset of what was consistent with the onset of color transparency for mesons, for both pion and rho electroproduction. And so that's what you see here, and you can take note that this onset is basically just on the order of a few Jev squared, right? So, so this started to kind of excite people because we were thinking if we can see it, then we should be able to see it in protons. So the first attempt to measure the onset in protons was done at Brookhaven using large angle proton knockout. And so here they measure the transparency as the ratio of the quasi-elastic cross-section from, in this case it was aluminum and carbon on versus the PPA elastic cross-section. And so they measured the transparency, and we're very excited to see this initial rise, as you see, of the transparency. But the effect could not be explained by color transparency alone, because as you went to higher effective momenta, you had basically a drop-off that was kind of inconsistent with the predictions from color transparency. And so this could have been explained by other effects, such as nuclear filtering or perhaps the edge of a new charm resonance. But it also, proton P2P scattering also has the added complication that you have to include basically the initial proton in your transparency extraction, because it has a reduction of flux as well. And so this got everybody excited in the community, EE prime P scattering, where you only have the proton in the final state. And so, so this was, a huge effort on many different experiments, and showing here you have data from both SLAC and JLab, showing that for a range of nuclear targets, ranging from deuterium to gold, we actually don't see this onset that we would have expected to see as a function of the momentum transfer. And significantly, this went all the way up to a Q squared of 8 Jev squared. And so the idea is, of course, is that the onset of squeezing between different reaction mechanisms is a bit difficult to translate. And so if you were to take the T value from the proton knockout experiments and try to relate it to the electron scattering Q squared, then you would have said that we would have expected to have already seen this effect in the 6 GeV era. We would have expected to see this rise, and we didn't. But we can't rule out the ambiguity that they had access to much higher proton momentum. And so that led us to the 12 GeV era. In the 12 GeV era, so this is a picture of Hall C. So you have kind of the traditional high momentum spectrometer, which was commissioned in the 6 GeV era color transparency experiments. Now we built the super high momentum spectrometer for the 12 GeV era experiments. And so this spectrometer was actually commissioned using the proton color transparency experiment that I'm going to tell you about that we ran. And so these are the detectors that you can see inside, and a huge effort on my part was really commissioning the optics and getting the tune right of this spectrometer, not only for this experiment, but for all the future experiments at the 12 GeV era in Hall C. And so that's what you can see here, is that we were initially tuning everything using, even we could observe the excited spectra of carbon and the SHMS. So even with this increased proton momentum, there was no observation of the onset of color transparency, and this was really a surprising result. So what you see here, we only measured on carbon, and you can see the previous data, you can see our data, and you can see that we already measured up to proton momentum up to 8.5 GeV, which was well within the range of the Brookhaven experiments. We also exceeded the Q squared all the way up to 14 Jev squared. So this had a lot of people scratching their heads, So we organized a workshop and brought all the theorists and the experimentalists together, and we had to really try to understand where to go from here. How do we interpret this data? So probably the overall kind of suggestion is that there was no point-like configuration that was really formed in these experiments. Probably the squeezing didn't work. We were measuring the Feynman mechanism process in this type of experiment. However, it should be noted that all of these previous EE'-P experiments, we used pretty much the same kinematics. So we were trying the same strategy, just with higher momenta. And so in these same kinematics, we're also susceptible to the expansion effects of this point-like configuration. It's time for a new idea, new strategy. And so that was what we proposed and was approved by the PAC last summer. So we proposed basically that we needed to change both the kinematics and the target to really fully evaluate where we would not see color transparency for the proton. So we proposed this color transparency and maximal scattering kinematics, where we can use deuterium, because deuterium has well-described final state interactions and double scattering through the generalized dichronal approximation. We measure the knocked out proton, and we can reconstruct the neutron, and we can base all of our kinematic choices on that. So if you look, basically in this experiment, we do things a little differently because we're actually measuring the final state interactions and looking for a reduction. So this is different from the previous experiments where we would have looked for basically an increase in transmission of unrescattered protons. Here we're looking for a decrease in the transmission of rescattered protons. So as you can see on this plot over here, we can basically choose, this is the angle between the neutron and the Q vector with the scattering electron. And so we can basically choose kind of the kinematics where we can enhance this contribution from rescattering kinematics. And rescattering kinematics is, of course, even enhanced more for the different initial neutron momentum. We can enhance our signal of color transparency in this scenario by taking the ratio between the kinematics where we would expect there to be a high contribution from rescattering to a contribution where there's low rescattering, and we would expect this ratio to go down, basically, if you have color transparency effects. So this enhanced sensitivity, then, is kind of what's shown here. So you see the ratio as a function of Q-squared. While we're not probing a new range of Q-squared, we're sensitive to much smaller point-like configuration lifetimes. And so it should be also noted that this experiment also gets around the loophole of the rapid expansion, because we can actually disentangle the expansion of the point-like configuration from just observing it. And we do that because in rescattering, we have basically that the larger the spectator momentum, this shortens the distances between the production and the rescattering vertices. And so this measurement could also have implications and help, perhaps, estimate energies needed, for example, on heavy ion collisions to produce weakly interacting quark-gluon plasma. And so in the near future, before this other experiment runs looking for protons, we're going to go back to the pion. And we're going to extend and confirm the onset of color transparency in the pion. We're going to extend, basically, we have to look for both the transparency and the nuclear A dependence alpha as a function of the Q-squared. And so we expect that this will help us to really tease out if we've seen the onset in the pion and what that slope would look like. But while we wait for the next generation of color transparency experiments to run, we build. So just as we had to commission the super high momentum spectrometer to accomplish even higher proton momenta, we push the limits in Hall A at the moment running the SPS form factor experiments, which are measuring the proton and neutron out to highest Q-squared values with extreme precision. And so in this way, I've been basically assembling, commissioning, and running a huge swath of gem detectors that we have for these experiments, because we need to cover the large areas, have very high resolution tracking. And so this is a huge effort on our part, because not only are these gems running at some of the highest rates times area for some of these full single foil large area gems, but we also have a huge number of them. This was really the first time running this kind of number in these types of experiments at the lab. And so I'd like to emphasize that it's when we try to build kind of the next generation and do the next impossible thing, it really takes a village and hopefully inspires the new physicists that will be coming on the scene in the future. And so looking toward the future, I also serve as a co-convener for the user learning in the software working group for the EPIC detector. So I serve basically the community, hoping that we can kind of make the ideal software that we all wish we could have had, so that everybody in the international community, everybody is capable of doing the analysis and extracting the physics in a timely fashion. And so, just to close this talk, I just wanted to say that CT is only one way to look for a direct transition rate from quarks to nuclei. But we can explore for evidence of QCD in nuclei from other observations, just to name a few. And so we can test the limits in our descriptions for helium in A+3 nuclei, like helium-3 and tritium, of which we'll be running in the near future again. We can study nucleon pairing among shells and nuclei, which we have 2 experiments that have already run, collected data, will be out soon on the calcium-40-48 isotopes with iron. We can also look for the origins of the EMC effect with respect to nucleons and short-range correlations by using deep and elastic scattering on deuterium. And finally, we can also test all of our assumptions in electroproduction by going to photoproduction and looking for color transparency there. And finally, I'd just like to conclude this talk by thanking all of you for your attention. And I would like to really thank all the people who have mentored me and supported me to be able to ask the kinds of questions and pursue my passions. And I would like to especially also thank all the wonderful students, postdocs, and collaborators who have made it really possible to push these new boundaries of physics as we kind of tackle these really tough experimental questions. So thank you.
Very good, thank you, Howie. So we'll now move on to our next awardee, Javier.
Thank you. So thanks a lot. I would like to start by thanking the selection committee for this award. I'm deeply honored to receive it. Also to thank all the other sponsors that make it possible. But especially to thank all my collaborators, the people that I had the pleasure to work with, because of course without them it wouldn't have been possible to achieve the results that I will talk about. And it's especially an honor to receive an award that is dedicated to the memory of Fred Olness because of the size and importance of his contributions to the field. I mean, it was not only about not only the high quality of his research, but also the quantity, the amount of subjects that he could cover. It is really amazing, and as it's written here in this quote that I put here, he was really a true giant of particle physics. Now, when it comes to the connection of my work, which is the topic I went very quickly, but it's about precision calculations in Higgs boson and top quark production. Really, I mean, his studies on the structure of the proton, especially with the development of the so-called D-Club equations, really set the basics, the groundwork for the development of all precision calculations that we do afterwards. So, I mean, it's really his influence, cannot be overstated. Now, as you can imagine from the title, there will be quite some overlap with the talk that we had in the morning from Mathieu, but I will go quickly try to show you what the main highlights of the things that I've been working on. But before going to the physics, I mean, even if this is to honor Guido's memory, I would like to take 1 minute to honor the memory of Stefano Catani, who passed away this last January. And while I did not have the pleasure to meet and work with Altarelli, I did have the pleasure to work with him, and I consider him another true giant of particle physics. Not only that, but also a wonderful person that everyone that knew him and got the opportunity to work with him will really miss him. So, yeah. So let me now go back to physics. So as I said, I will be talking about precision calculations. And really, I mean, for me, the crucial thing is that these calculations are really crucial in the quest for new physics, especially in the current landscape with the LHC measurements that show no clear sign of deviations. It's really with advanced theoretical tools that we can really explore and fully exploit the wealth of data that we get from the LHC. And these tools and these predictions can be the factor that determines whether we discover a signal or we miss it among large uncertainties. So I'll focus on two particles, which I think are among the most interesting particles that are being currently studied, the Higgs boson and the top quark. The Higgs, of course, the latest particle to have been discovered or from the particles of the standard model, and it's responsible to the electroweak symmetry breaking. And of course, this is the least explored sector of the standard model, and it's very interesting to try to see if we can find some new physics signals within there. And there is the top quark, which is also special in connection with the Higgs, because otherwise the top, it's really, in terms of its interaction, is quite normal. The thing that makes it special is its mass, so its interaction with the Higgs field. That has all types of consequences, right? So, for instance, the exact value of the top mass has an impact on the stability of the standard model vacuum because of the large corrections that it induces due to the big interaction with the Higgs. It has also, there's an interplay between the two, because since the main production modes of the Higgs boson are mediated via a top quark, it also has an impact on Higgs observables. And being the heaviest particle of the standard model, it has also some interesting features. For instance, that it decays is the only quark that decaying before ionizing. And it can also be the gate to new physics, and also it's the background of lots of searches at the LHC. So it's really important to get precise predictions for Higgs and top processes at the LHC. So we'll first talk about Higgs per production. As you've heard before, this is kind of the picture of what we know about the Higgs coupling so far. And you can see that here we don't have a data point for the Higgs self-coupling, because we are not there quite yet, because of the challenging measurement, because of the small cross-section associated with di-Higgs production. That is one way to directly access the Higgs self-coupling, and therefore to explore the Higgs potential. Because this self-coupling, of course, arises from the Higgs potential after symmetry breaking. Now, as it happens for single Higgs, the main production mode is loop-induced gluon-initiated production via a heavy quark loop, namely the top quark. And as I said, that we don't have we have bounds. So far, we have a bound for the cross-section which is about 5 times the standard model cross-section. And the future prospects indicate, as you heard earlier today, that it can be measured at the high lumen LHC. So for Higgs per production, the full N and LO corrections are not available because it's a really difficult process. It's a loop-induced process with multiple 2-to-2 process with 2 masses in the external, in the final state, plus the mass of the top in there. So it's really at the frontier, a bit beyond the current state of the art. So what we do in this context is to try to compute things in approximation. So what we did is to first compute the next in order corrections in the so-called heavy top limit, where you integrate out the top loop. And then we had to improve this, because of course this was not enough for the level of accuracy that we aim to obtain. So we developed some reweighting technique that allowed to incorporate partial finite top mass effects in our calculations, so that the most that was available at the time. Then we further combined this with the full inexorably nodal corrections, threshold resonation effects, in order to achieve the ultimate precision that was available. I know that more recently there were some further developments, like NQ-below in the heavy top limit, that became available more recently than these results I'm presenting now. And you can see the effect of, it's hard in the screen here to see the bands, but there is the gray band, it's around here for the NLO uncertainty, and you can see that the NLO uncertainty is much smaller, corrections of order of 10%, but they really help to shrink the uncertainties, which is what we are after. So one could say that in terms of the QCD expansion, we have a good control of the metropolitan uncertainties at the moment. There's one interesting thing that also serves as a connection to start talking about the top, which is the last slide of the top, which is, as I said before, the interplay between the Higgs and the top. And in particular, it was noted a few years ago that there are big uncertainties in Higgs per production, coming from the ambiguity that exists in the choice of the renormalization scheme of the top quark, whether you renormalize it in the on-shell scheme, for instance, or in a scheme in which the top mass runs, like the MS1 scheme, and the specific choice that you make for the scale of this renormalization. And it was observed that actually this source of uncertainty is at the moment the dominant source of uncertainty for Higgs per production. And it's the case also not only for Higgs per production, but also for Higgs production when the Higgs is produced off-shell. So these uncertainties are very small for the physical Higgs boson mass. But as you increase it, these become very large. So for instance, they will affect off-shell Higgs production. So this issue is still there. But we did study the effect in single off-shell Higgs production at next to next in order, including full top mass dependence. And we showed that the inclusion of the NLO corrections allowed to reduce this ambiguity. And this you can see in these plots by going from leading next to leading and next to leading and comparing the orange and the purple bands, how they become closer to each other, and more importantly, that they become narrower and narrower. So the difference between the two schemes is significantly reduced at NLO. So with this, let me go to the top. So we talk about the Higgs and the top interplay. Now let's talk about the top quark. So as I said before, top quarks are produced a lot in the LHC, about 15 TT-bar pairs per second. The TT-bar production is the main production mode. And in this context, what we did is to work in the QT subtraction method, a method to deal with the infrared divergences that appear in the intermediate steps of a fixed order calculation. And this method was originally developed for the Aharon production of color singlets, and now we extended this method to be able to deal with the production of heavy quarks, which is illustrated here. Essentially, you need to account for the extra emissions that connect now all your particles, your partons in the initial state and the heavy quarks in the final state. And now all of them are colored particles, so you have the emission between all of these particles, and they lead to new divergences when these emissions are soft that you need to take into account in order to be able to develop such a subtraction method. Thanks to this, we performed an independent calculation for TT-bar next to in order and released the first public code within the matrix framework that is able to produce NLO distributions. And we also obtained distributions in the MS-bar scheme using a running top quark mask and used those results to extract the running using CMS data, as shown here in this plot. And now, if you really want to do the connection with the experiments, fixed order calculations can only take you so far, because in the end, what you really need, the theoretical tool that you need, are really event generators, right? A tool that is able to fully mimic a realistic final state as it is observed in the experiment. And luckily, let's say, in close connection to the results that I showed you before, these results that we developed for QT subtraction, we were also able to apply them in order to, after doing some extra work, to develop a tool, an NNLO accurate event generator, so a matching of NNLO and parton showers for heavy core production as well. So in particular, we extended the so-called NNLO-PS method, again only valid for color singlet, to deal for heavy core production. And this is the first case and the only case so far of an NNLO-PS generator that goes beyond color singlet. And you can see here in this plot, I just showcasing some of the results that we get for the different decay channels of the TT-bar system and the comparison to data. And you can see in general a good agreement. And the nicest thing is to, I mean, this of course is a public generator, and the nicest thing is that they are being used already by the experimental collaboration. So here, this is some plots from an atlas measurement, and you can see here that they are comparing the previous generator only NLO accurate with the purple one, the NLO accurate one, and you can also see here improvement. And then, final slide. Then afterwards, we extended this a bit more, in both sides, the fixed order side and the quantum shower matching side, in order to deal with final states that involve a heavy quark plus a colloidal final state, such as, for instance, TTH production, TTW production that were mentioned before. So in particular, we managed to obtain a method that can deal with this kind of processes. Of course, the bottleneck right now are the two-loop corrections, and the particular cases of TTH and TTW, we managed to find a way to approximate these missing two-loop corrections in order to obtain predictions, accurate predictions for the LHC. And you can see that we really break down here for TTH on the left, the perturbative uncertainties a lot, and on the right for TTW, we have here a prediction that, this reduced uncertainties, theoretical uncertainties allow for a better, a more meaningful study of the measurement and this small tension that it is there for the TTW measurement. And as I said, these developments go hand by hand with the developments on the NLOPS side and processes of this type, the release of processes of this type is underway, and here is some preliminary results for TTH within the NLOPS method. So with this, I arrive to the conclusions. I hope I try to tell you how these advanced theoretical predictions are crucial to explore the physical potentials of the LHC. I told you about some things in Higgs and copper production. There are still some things to improve. As I said, this scheme uncertainty in the Higgs. On the NLOPS side, we still want to maybe to improve the treatment of the decays. Eventually, we would like to include also non-resonant contributions. For these things, the method is there. The current bottleneck are process-dependent two-loop amplitudes. And I would like to emphasize that event generators are still behind the fixed order progress, because we have fixed order predictions for colorless plus jet, like Z plus jet, Higgs plus jet. We have predictions for Higgs and Radian at NQ below, but we don't have event generators for that. This is the next goal that we should try to tackle. And here, of course, this was not, I want to say this was not an overview talk, so I just highlighted my works here. See an overview for a full picture, and even more relevant, there are many other tech signatures that are relevant for the LHC, and to attain the level of precision that we need is really a community effort. We need to keep working towards it. So that was all. Thank you for your attention.
Thank you, Javier, and that will conclude the Altarelli Award Ceremony. Let's, again, I want to say thank you to our sponsors, but also let's one more time congratulate Holly and Javier, please. And now I'll turn it back over to our chair, Juan.
Thanks, Fred. So now we have two more talks to end today's session. So the first talk is by Professor Yuki Yang. Hopefully the slides will be okay. Have the slides.